Okay, I'm going to walk you through our Java implementation of the A-star algorithm. Here's a map of Duluth that's included in this project. So Duluth has kind of a strange street layout because of the lake and all the rivers and parks that feed into the lake, so we don't have the traditional grid. And so it's a nice pathfinding challenge. So I've just put little nodes at some of the major intersections around town so you can find things, directions. So here node 1 is called a St. Scholastica, like node 11 is the mall. So if we wanted to go from St. Scholastica to the mall, we're going from 1 to 11, and there's no great direct path. So there you could go up here, go over here, you can go here. And it may not be obvious what the shortest path is. The shortest path is actually to go down here over to 11. Okay, so let's look at how this is done in Java. So we have our main controller. This is just a bit real simple interface. I've tried to keep this very simple. Just ask what node do you want to start and what node do you want to end, or is your goal node. So like in this case, if we wanted to go from Scholastica to Mall, we'd go from node 1 to node 11. And then it initializes a map. There's a map class here. This just kind of implements this actual map as a data structure. So it works with these node objects, and each node object keeps track of its coordinates on the map, its physical location, and then we also have information about how each nodes are connected to each other, that you can go from node 2 to node 3 and from node 3 to back to node 2, and then the distances of all these areas. So we know the distance, all these, like this 1.5 from 9 to 6, that's recorded. All these distances are recorded in this data structure here. It makes use of a node structure or a class. Again, it just keeps track of each node's on the map, where it's at, its X and Y coordinates, and some information about it. Some of this stuff we'll get into in a little bit when we talk about pathfinding. So we have our map in our main controller. The next thing we create is a pathfinder. This implements the actual A-star algorithm. Let's, let's open up the right file here. Okay, A-star. The main thing in A-star is this calculate shortest path, which it's going to try to find a path and hopefully find the shortest path. There are some errors in it that we'll see that you'll want to correct, and these are part of your participation problem and your assignment this week. But let's just compare this to the actual algorithm given in by the standard videos. So in there they have a frontier list and an explored list. The explored list starts off as empty, and they loop while the frontier list is not empty. So let's look at the code here. So going up a little bit more. Okay, so we start with an empty explored list, an empty frontier list, and then we add the start node to the frontier list. So this gets us going. We have an explored list and a frontier list. These are just array lists of nodes. That's what these two things are. And then we say while the frontier list dot size is not 0, while there's still stuff on the frontier list, we're going to do some things. So that's very similar to this. Again, we initialize the frontier to our starting node. We start with an empty explored list, and then we work while the frontier list is not empty. Now we're going to grab a path or an item from the frontier list and add it to expand it and add it to the explored list, and then we're going to test to see if we've reached our goal. So that's what we're doing here. We're going to grab the next item from the frontier list, and we'll look at different ways of sorting this frontier list in the assignments this week, but we're just going to get the next item off the frontier list. And then we're going to check if that is a goal, and if so, we're going to quit and return. We have to reconstruct this path we found as the shortest path. Otherwise, if we're not at the goal, we're going to remove the item from the frontier list and add it to the explored list. And then we're going to do some calculations now on this item to make sure we update it. So again, we look at we're updating this frontier. We look at the path so far and then the new action, the new step we have. So if we're taking another step, we add that to the frontier list. And that's what this does here, and adds this in. Let's try a simple example of this. So I'm going to run this program and go from node 1 to node 7. So I'm just going to run it, type starting at node 1, going to node 7. It should find one of these two paths here. And again, it's not optimized yet, but it'll find a path certainly. So let's look at what this is telling us as we go. So again, what the method will first do. Okay, so the first thing we do is we clear out our array list in case we're running this again, and then we add the start node to the frontier list. So we have these two lists, and we're adding the start node, and we said that would be node 1 to the frontier. And then we're looping while the frontier list size is not 0, and again, there's something on the frontier list, so we're still searching for a path. And then we're going to look at the current node and grab that. So we're going to keep track of the current node. It's number 1 here. And then we're going to keep track of our goal. Now we said it was going to go from node 1 to 7, so current is not the 7, so we're not there yet. So now we can start our loop. We're going to remove this item, the current node, from the frontier and add it to the explored list. So 1 pops off here and is added here. And now we're going to look through this. So what are the different actions we can take? What are the different neighbors of our frontier list? So let's look at our map again. From 1, we can only go one place, to 2. That's our only option. So we add that to our list. So again, for each of the neighbors in here, we get the neighbor and use that. We print out that we're checking that neighbor, and then we add, we check if it's already on the explored list, and then we do some calculations for distances for that. So for example, here we say 2 is now one of our neighbors, and its distance is 0.5 from here, and there was 0 distance from the goal to 1, I mean the start to 1, because 1 was our start. So to get to 2, we have 0.5 as our distance. And we check if the frontier list contains that neighbor. Does the frontier list contain 2? Nope. So now we're going to add that neighbor to the frontier list. We're going to add 2 to the frontier list. And then we're going to mark some things where the previous node was, where we came from, the distance from the start here, and this is where you'll be doing some changes in your code here. So we've added 2 to the frontier list. Now we're going to go back up here. Okay. Yep, we loop back up here, and we loop up a little further here. Now we check if the frontier list size is 0. Nope, there's still an item on the frontier list. We're going to grab the current node from that, so now the current node is going to be 2. Is the current node the goal? Nope, we're trying to get to node 7, and we're at node 2, so that's not there. So we're going to remove it, the current node, from the frontier and add it to explored. So we're going to take it off of here, and we're going to add it onto here. And then we're going to look at all the neighbors of our current node. So if I look at our map, from 2 we can go back to 1, we can go up to 3, 4, and 6. So those are our 4 neighbors that we can work with here. So maybe we'll just keep track of our neighbors here too, because we're going to loop through all 4 neighbors. So our neighbors are 1, let's see, what were they again? 1, 4, 1, 3, 4, 6, 1, 3, 4, and 6. So we're going to loop through each one of those as we go. So we've got the neighbor, we print out information that we're checking that neighbor, we check if the neighbor's on the explored list. So again, we'll do this neighbor 1, and that's on the explored list, so we'll just get rid of that right away and continue our loop. And now we'll go to the next item, which is 3. So it's not on the explored list here. So we calculate the distance that we've traveled so far plus this new distance. So in our map, the distance to 2 is 0.5, and then we add on this new distance to 3, which is another 0.4. So now the distance from our start to node 3 will be 9. We'll calculate that. Now we check if the frontier list contains the neighbor. Nope, it doesn't. So now we'll add that neighbor to the frontier list and update some of the distances. So we'll add 3 to the frontier list. And if we go through this again, so now we'll loop back and go to the next neighbor and next neighbor, and we'll add them both to the frontier list. So 4 and 6 will both be added to the frontier list. And we can actually see how this is working with some of the printouts of this algorithm. So again, it says grabbing node 1, calculating the shortest path from 1 to 7. Grabbing node 1 from the frontier list, we did that, and it updates some distances. And it then checks neighbor 2, and it adds it to the frontier list. And then we just grabbed number 2 from the frontier list, that's what we just did now. And updated some distances. And then we're checking node 1, already on the explored list. Node 3, add it to the frontier. 4, added to the frontier. And 6, added it to the frontier. So now we have 3, 4, 6 all added to the frontier. So next thing it's going to do is it's going to, oops, went up too far. Again, we're checking if the frontier list size is 0, and now there's still item on the frontier list, and so we're grabbing the next item off the frontier list. Eventually we'll do some sorting of the frontier list, but right now we're just grabbing the whatever's in the first spot on the frontier list. So again, now we're grabbing 3 from the frontier list. That's our current node is now 3. And we look at the neighbors of 3, and if we look at our map from 3, oops, we have to scroll up a little bit, we can go to 2, 7, 8, and way up here is 22. So 2, 7, 8, and 22 are all the neighbors that we'll look at. Now we check each one. 2 is already on the explored list. So we don't have to do anything with it. We've already explored 2. We don't want to go back there necessarily. 7 is added to the frontier list, so we add 7 to the list. And that's our eventual goal, so we know that. And then 8 and then 22 are all added to the list. And then you can follow through here. The next thing it's going to do is take, okay, so we took 3 off the frontier list. And made it our current node. Now we're going to it's going to take 4 off the frontier list and add. It's going to check node 2 is already on the explored list, but it'll add 5 and 6 to the frontier. When it's doing node 4, and again, oops, we've explored 3. Now, once we're done with 4, we'll pop 6 off the front. Oops, I should have deleted 4 here. Now we'll plop 6 off of the list and make that our current node. So here we've got 6 that we're exploring. And again, this is just what this algorithm is doing. We're checking if the frontier list is 0. Oops. And it's not. We're grabbing the next item from the frontier list, was what's that, 6 that I just grabbed or deleted. And then again, we always delete these from the frontier list, add them to the explored list. So delete the 6 from here and add it to the explored list. And then we look at all the neighbors of that node. So the neighbors from 6 are 2, 4, and 7. And then again, 2, 4, and 7. And for each one, we are going to check if the neighbor is on the explored list. And if so, we're just going to continue with the loop. So in this case, 2 is on the explored list, 4 is on the explored list, and 7 is already on the frontier. So we do nothing in this case. And then finally, we will go back up here and we'll grab the frontier list is still not 0. We'll grab the next item off the frontier list. That's this 7. So our current node is 7. Add that to the explored list. And then we find, is 7 the goal? Yes. So now we found our goal, and then we can reconstruct the path that we used to get there. Okay, so that's the basic workings of this Java implementation of A*.